Okay, so I guess we start now. So last day, 2 weeks ago, I discussed the existence and uniqueness of the strong solutions to the Euler equation. So we were dealing with this equation. With initial data in L2 sigma, where sigma means that it's divergence free. And we proved the theorem that for initial data in HS with incompressible conditions, S bigger than dimension of R2 plus 1, then there is a time and there exists a unique solution solving Euler, which was continuous in HS. And C1 with one derivative less because of this loss of derivative. And we didn't really finish the proof, but the steps that we followed were 5. Basically, it was a standard modification argument. First, we modified the equation and we defined the Euler epsilon equation by this form. With initial data the regularized use. And here it was important that we have a modifier both in this term and this one, so that when we integrate the facts, we have the gradient of the function times the function. And this was the main point that gave the cancellation of the higher order term. And for this equation, for the regularized equation, we show by a fixed point argument that there was a unique solution in this case. Then, in this first part, this was only, this was the epsilon, up to a time that might depend on the parameter epsilon. So in the second step, we show that we can take the epsilon to be infinities, in particular, all the regularized solutions live in the same time interval. Then we did uniform in epsilon estimates. In particular for u epsilon in n infinity time. HS and for the derivative. In one step. And now here the time was already uniform, doesn't depend on epsilon. Because of this uniform estimate, we prove a strong convergence by showing that the sequences was Cauchy. and we prove that it's Cauchy in a lower regularity state, which together with weak convergence in the high regularity was enough to do step 5 that we didn't do, and we have to do it now, that the limit object actually solves the equation. Okay, so this is that u epsilon converges to some u, and now we have to prove that u solves the original equation, that it's unique, and also the remaining point is that it's also continuous in time in the higher HS. So my intention today is to prove the same results for Navier-Stokes. So that way we will basically review all these steps. I will only show the difference for 1, 2, 3, and 4, and I will make a step 5 from C. And once we have that, in the second part, depending on how much time I have, we will show existence of weak solutions for Navier-Stokes. So basically the first theorem that I'm going to prove, which is this one for Navier-Stokes, is far from sharp because we are asking a lot of regularity for the initial data, and we can do better in the case of Navier-Stokes, which will be the second part of this lecture, and probably on the fourth lecture I will go back to that. Okay, so the only difference in the equation is this term. So the theorem is going to be exactly the same as there. Okay, with the same space. The solution will live in the same space. And now for the proof, as I said, I have to repeat all the steps. Well, the only interesting point of this theorem, since as I said we can do better than this, the goal of this is that all the estimates that we obtain on the time of existence will be independent of nu, of the viscosity. So the solutions that we obtain here, because of that uniform in viscosity, will be convergent to the solution of A. So this theorem says that for a smooth initial data, one can approximate the solution of Navier-Stokes for a small viscosity by the ones by A. Okay, so in the first step, what we did last time was write this equation in integral form, well, the modified equation. So this part I will keep it in the same form. Here I'm using the same notation as the other day. J epsilon is the operation of convolution with the modifier T epsilon. And now I have to modify the viscosity here. So I have to decide how I modify. And the one that will work, and we will see it later, is putting two modifiers. And the reason is similar to why we put one extra here. So that later when we try to do the energy inequality, one of these modifiers will move to the other side. Yes. Now, because I want to use some of the estimates of the other day, this part here, we call it capital F the other day. And this second term, I will just keep it like this. And all this thing here, we write it as a fixed point, so an operator applied to the US. And now we want to construct the ball here. As I did the other day, the only new thing is to show that this term is bounded at ellipses in HS. And then one can choose a small time and a small ball where we can close the epsilon. So we have to show that this quantity is bounded, and that its ellipses, which is almost is basically the same. And this is just using the properties of the modifier. And it's not working, then or maybe it's the batteries. Maybe it's the batteries. The other day she brought some, but for the camera, I don't know which kind of battery.
Just double A.
These are big, no?
It's triple A. Yeah, actually, it's triple A.
No, but these are bigger.
Yeah, that's deep. Yes, you have triple A. It's the block. It's not that.
So it is working or?
Yeah, it's wrong.
Vale.
Look at it.
Okay, so then I continue. So I was saying that for this estimate, we use the properties of the modifier. So basically, we bound the derivative paying a factor of epsilon. So because we have the derivatives, epsilon squared, epsilon h. And here, do the same. So we can construct a fixed point on the time interval. We can choose the time t epsilon sufficiently small depending on nu, epsilon, and the norm of the initial data. And we find a fixed point u epsilon in the ball of radius R, and in particular, the other day we showed that we can take the ball of size twice the one of the initial data. Now the second step was to prove that we have a common time interval for all the solutions, and in particular that time interval is infinite. Okay, and this. Okay, so this was a consequence of the energy inequality, and then also bound the HS norm using this formula here. So on one hand we have the new term the camera stop here, the camera stop here, right?
Yes, yes.
This is minus. So here I'm already going to integrate by parts. Also the modifier, we can move it to the other side. That's why we put two modifiers here. And in this step here, as the other day, we use the incompressibility property to cancel the higher order term. And to bound the HS norm so that we can guarantee that we can continue solution, we do it from here. And nothing changes from the other day, because as we have done right one step before, we can pay a price of epsilon. And at this moment, we just want a bound for every time, and we don't mind if this bound depends on epsilon or other quantities. It's in the step 3 when we want to obtain uniform bounds in epsilon. And for that, we have on one hand the L2 energy inequality. Now we have to do the same one in HS. And from the other day, I copy what we obtained. HSQ. This came from U epsilon HS squared gradient of U in L infinity. And this was the main, basically, this was the step where we used crucially the condition that S was bigger than D half plus 1, so that we have the embedding into HS. And today we have an additional term, which is the one coming from the Laplacian. Let's put S derivative. I'm going to denote it like this. Okay? You can think it in Fourier if you prefer. But this term is harmless, because as we have done in L2, we can do the same iteration by parts. So this is minus nu gradient J epsilon d epsilon in HS squared. So this gives a uniform bound for U epsilon in L infinity HS, and for the derivative we use the equation, and the other day we lose one derivative, today we lose two derivatives, so this is uniformly bounded. HS minus 2. And here T0 was chosen from this inequality. We have a cubic inequality, so we solve it, and we could choose T0 equal to, this was, so we obtain from here some constant time. In particular, we could choose T0, not. So independent of nu and independent of epsilon. So notice that all the steps we are dealing with the Laplacian as a perturbation. We are not really using it, which is not the smart thing to do, but on the other hand, it gives a time that doesn't depend on the result. Okay, that's step 4. I'm not going to do it because we did it the other day and the Laplacian doesn't have any complication. We show that U epsilon is proceed in L infinity, sorry, in continuous 0 to not L2. This can be done exactly like the other day. Write U epsilon, U delta, and do an energy balance, and then use Gromwald. But to close that balance using Gromwald, we needed quite enough regularity. So we needed in particular to use the HS, which is at least H2, because S is bigger than dimension half plus 1. So in this process, we were using that we had enough regularity. And also we use the weak convergence in the higher one. These two together gave us a strong convergence in all the intermediate norms by an interpolation. So with R less than S. But since epsilon is strictly positive, this still controls gradient of U. This strong convergence guarantees these conditions that we need for step 5 that I'm going to do now. So here is where we stopped the other day. We want to show that the limit object U solves the equations. What we know so far is that U epsilon solves it. So we have this expression here. Well, it holds for R bigger than 0, no? Because we have it in L2. Bigger than 2. I need it for bigger than 2 because it will appear, well, here this is L infinite of, so you have, and also now, these estimates, apart from this, we will also need the H2 norm. So it will appear. I'm using H. Well, it depends on the dimension, but okay. Yeah. So we know U. So we know this, and we want to show that this is also true for U. And what we are going to show is that this is true in the L2 sense. I want to show that the L2 norm of this is goes to is equal to 0. So I'm going to take the difference on these two, and I will estimate the L2 norm and make epsilon going to 0. And now I have to do the difference, so many terms of this minus this one. And to get that everything goes to 0 when epsilon goes to 0, I will use basically two facts. One, this strong convergence here. So every time that we have a term like u minus u epsilon, we use this convergence to show that it goes to 0. And then we have to use also the modifier. So for example, let's start doing all these splittings. This is something nice for the strong convergence. Same with this one. Now we have u epsilon, and we start subtracting this one here. And in all these kind of terms, we will use that this goes to 0 because this is a modifier. So we will use kind of a mean value theorem to obtain a power of epsilon by paying one derivative here. Okay. And finally, the term with the Laplacian. Vale. So now we group everything. For example, the first one is just this one. Then the one by the initial data. Okay, so for this one, we can put this in L infinity. For the second, we can do the same. Here, for example, appears this condition here. And now for each one of these, as I said, we put a factor of epsilon and one derivative more in this term. This was L2, so H1. Now this one here, I put this in L infinity. This in L2, so this is epsilon, epsilon in H1. And this one here. Let's put this in L infinity. This in L2, so H1, one more, so H2. And then the term of the Laplacian nu, well, this I don't take it, it's just u minus u epsilon in H2. And now this one here, I cannot use, I mean, it's the same, but I cannot just take one factor of epsilon and one more derivative, because they don't. Then I would need H3, which I don't have. So, well, I do this estimate. I can do it here just very quickly. For example, in Fourier, it's immediate to see it. If we write the L2 norm of this, we write it in Fourier. We were using these modifiers the other day because we have twice. Okay. Twice. And now, what I am saying, yes. Yes, so simply multiply and divide by this one. Now, this is bounded, so we are, as always, putting alpha derivatives, paying a factor of epsilon to the alpha. We did this all the times with power 1, but we can do it also like this. And also, if you prefer, you can work in physical space, but I think it's faster to see it this way. So we have nu epsilon to the alpha, u epsilon h2 plus alpha, and we take alpha so that this 2 plus alpha is smaller than epsilon, something that we can do. And now send epsilon to 0, and all the terms here goes to 0 by the strong convergence, and all these ones goes to 0 because of the factor of epsilon. Okay. So we have proof that this is in fact true, that the limit object U solves Navier-Stokes in the L2 sense, in particular for almost every x and t. And then to prove that it's also for at every point, use the regularity that we have to show that each one of these terms is in fact continuous. The strong convergence is up to here, so we can take R equal to 2. Okay, so we are almost done. We have finished this part here. We need to prove that it's unique and that it's continuous in the high norm. So that it's unique is very, very easy. Just use the take L2 inner product and we obtain. So take two solutions, U and V, with the same initial data. And here we have Now one of the two terms, this term here, cancelled by the incompressible condition. We used this a lot the other day, and this one we can just round it, L2, L infinity. And now by ground walls, since we have ground walls, we can use that we have this quantity. So because this is 0 times 0, we conclude that the solution is unique. Now the second part is more tricky, this one here, to prove that this is continuous, and I will skip part of it. So, and we have to do it separately for Euler and for Navier-Stokes. But for Navier-Stokes, we will use what we prove for Euler. So for Euler, things simplify because the equation is translation invariant in time, so we can just prove it at time 0, and also the equation is time reversible, so we can study the continuity just from the right. So we just need to prove this one here. And this is not true for Navier-Stokes, because for Navier-Stokes, we don't have, the question is not time reversible. So once we have this, that will apply equally for Navier-Stokes, we also have to prove that we have continuity from the left. This one here, I will skip the first point, which is the more technical one. Although it's short, is proof that we have not continuity, but weak continuity. And if you want to see, this is in MIDA, in chapter 3. It's just like it's not too long, it's like half a page. Once that we have this, then because of the weak continuity, we have, okay, so this was, and here I'm not using that, just properties of the weak convergence, so this is true. And then to obtain the other part, I will use the estimate that we have from the energy balance. We knew that U epsilon E Hx was less or equal than U0 Hx 1 minus some constant in T, the initial data. So because this is true, let's take the limit sub in epsilon. So this is bigger or equal than U H epsilon, and then take lim sum in T. So here, this appears. So we have here and here, and we conclude for the Euler. And okay, for Navier-Stokes, we can also show that with continuity, do this argument. We have a continuity from the right. Now we have to prove that we also have continuity from the left. And to prove it, we will use the Laplacian that we haven't used so far. We will use that because of the Laplacian, we gain some regularity. So for positive times, we will have this extra continuity. So let's do it by contradiction. So assume that this does not hold. So let's construct a sequence of Tn that goes to T naught, for which this is bigger than some constant. So let's assume that it doesn't go to 0. Okay. Now let's fix some delta arbitrary and choose some n so that okay, so basically let's choose a t which is very close to t0 and we control it by delta. Now we want to use the dissipation, as I said. So the extra knowledge that we have here is that the integral from 0 to 0 of nu nabla u hs squared, this is controlled from the energy inequality before. So in particular, we have that extra regularity for almost every term. So u, this is tau, so u tau is in hs plus 1 for almost every tau in this time interval, for example, t and delta. T0. So let's choose one of these tau for which this holds and repeat the whole argument. So basically, we are starting Navier-Stokes at a time where the initial data is one derivative more regular. So repeating everything that we have done, we obtain a new time and in particular we know the expression of t tau, like the one before, for example. So one. Now here u at time tau hs plus 1. And on these time intervals, and some u, which is in L infinity time. I know continuous in HS. In particular, this is better than this. It's continuous in any HR with R less than S plus 1, like before. No, this is theta. So this is on tau, tau plus theta. Well, we are looking, sorry?
You don't reach T naught.
Well, no, not yet. So, what do you mean you don't reach T naught? So far we haven't reached T naught. No, this is now how we obtain the contradiction. So if this has reached T naught, then we have a contradiction because we said that this was not true. And now it's basically that's how we are going to finish. So, well, I say if this is, if we reach T naught, we have the contradiction. So assume that not, so we have that T tau plus T tau. This has to be smaller than T naught. Okay, and we have the expression of T tau. So T tau, I'm going to put what it is. 1 1, 2 0, h plus 1. This is less than T0 minus tau. Now tau I've chosen here. So in particular, this is smaller, smaller than T0 minus T and delta. And this quantity was smaller than 2 delta. So this is smaller than 2 delta. So we have that U tau H S plus 1 is bigger, no? Bigger or equal than 4, 0, delta. And this is true for tau, no? For this, ¿dónde estaba tau? For this tau set here, no? Un tau. Zero. And we conclude here by using Chebyshev inequality. So this is true on this interval, but now we know the length. We know that this interval has length less than delta. So let me check exactly. This is bigger than delta. Yes. Okay, so delta, yes, smaller than the set of taus for which the inequality holds. And this is smaller than 1 over this square. So this is the L2 norm. So we bound it by the whole thing. U tau just plus 1 square U tau. The thing is that this is bounded. This is controlled. So choose delta small enough so that this is a contradiction, because here we have delta and here we have delta square. Bye. Okay, so now the proof is complete. We finish with a smooth solution to Navier-Stokes. And as I said at the beginning, in all the estimates, the time interval was independent of nu. So this can be used to prove directly strong convergence of the solution of Navier-Stokes to the one by Euler when the initial data is smooth. And now we are going to, we have time more than enough. I don't know if I proved it the other day or not. I'm not sure if I proved it, in fact. So the L infinity here, so this part follows directly from the equation. Well, in fact, here is for Navier-Stokes is -2. This follows just from what you know here. And in Navier-Stokes, you have also the Laplace, no? You have the L infinity. But, okay. So the continuity is obtained, I guess you have to work a little, but it's obtained from, I don't have it written, from the Mine formulation. Like write this in integral form, and then you have the expression for ut, u0 plus integral from 0 to t. And then use the regularity that you have for all the other things, that you have the time integral and you obtain continuity. Yeah, I think that's one. Assuming the weak continuity that I also didn't. Okay, so the plan for the rest of today, the next on Wednesday and so on, is first now define weak solutions, the array of weak solutions, show that they exist, and comment things about uniqueness, that it falls into D and we don't know in 3D. Because of that, because of weak solutions, we don't know if we have uniqueness, then we will define the future lectures another kind of solution, the so-called mild solutions. And why? Well, because here, as I said, the initial data needed to be in too much regularity. We haven't used the Laplacian, so we can lower that regularity. If we lower too much, we will see now that we don't know if we have uniqueness. So we will reach a compromise, and we will try to obtain existence and uniqueness of solutions to Navier-Stokes in the optimal or best possible spaces in terms of regularity. And for that, just because this is a course, we will do it in best of spaces, so in a bigger family of spaces, and therefore next day I will start defining best of spaces and doing some standard estimates of partial differential calculus and this kind of thing that later we will use to show these solutions for Navier-Stokes. Okay. Okay, so I'm just going to write the definition of the array of weak solutions. So we impose that U solves Navier-Stokes in weak form. So multiply Navier-Stokes by a text function and then integrate by parts. So they have to solve yes, okay. And this for any text function. Also, this is, sorry, I didn't write, but this is the definition of the array of weak solutions. In particular, they satisfy the equation in weak form and they satisfy the energy inequality. No, I don't need. Okay, that's and they attain the initial data in another theorem by there. Which is in 34. So for you in L2 and just in L2 exists at least one weak solution. Well, one weak solution with initial data U naught. The solution satisfies the energy inequality. And for the time derivative, is in this space where PD depends on the dimension. Okay, so before proving the theorem, the system, I will show the uniqueness into D and why the uniqueness, and why that proof does not work in 3D. Well, the statement is the same. Okay, so take U0 and then assume there are U and V. U, V, weak solutions with initial data. And we are going to do as before, take do an energy balance and try to close by numbers. Okay, now multiply by U minus V. Assume that I can do that. Like I can test by U minus V that I will call W. Okay, this is the one that vanishes. This is the one that we had before. So this is I'm going to theory by parts here. So I'm going to write this in index for a second. This is WI partial this. Because of the incompressible condition, put it out in theory by parts. So this is W gradient of W times this one here. This disappears. And this was the main cancellation that it chooses for the system uniqueness of Euler, which is like here you use the structure of the equation. You have P, V, W, V times V. So write this in V is divergent free. So the projector here disappears. This is VI partial I WJ WJ. So this quantity here is VI partial I 1/2 WJ squared integral parts. And this is 0 by the divergence. So now we bound this. Okay, because we have the dissipation here, let's remove the gradient of W. So I will put this in L2. And once I've made this choice, I have omega and U in L2. So For example, L4 and L4. And I want to use ground one. So this L4, I want to transform it into L2. So let's use this is called the Lichtenstein inequality, which is a particular case of Gallardo, Nirenberg, all these interpolation inequalities, which is at the L4, and this is now for dimension equal to 2. So the L4 is bounded. I think there is no constant, but I'm not sure, so I'm going to put a constant. L to 1/2. One derivative, 1. And in dimension 3, then I don't remember. Later we compute with which is the exponent in dimension 3. But let's finish in dimension 2. Okay, so this is gradient omega L2 to the power 3/2. This is 1/2, 1/2, and also 1/2, no? So now jumps, or well, the typical one, no? Let's choose P equal to, I want this to becomes 2, so this is 4/3, and the dual is 3/4 plus 1/4, no? Well, and let's do it the version with an epsilon so that we can absorb this. So this becomes nu halves L2 squared, some constant that depends on nu, and we finish, no? So this gets absorbed by that, and then we want to deal with this with wormholes, so we have to control this quantity here, but by the energy inequality, this is just bounded by the initial data, and the time interval of this quantity also is bounded by the initial data. So basically, we finish. No, we conclude that this is controlled by this quantity at time 0, which is equal to 0. And I don't need to repeat the steps, but if you try to do this, well, I have to finish this part here, no? So if we compute these exponents and repeat the steps here, no matter how much we play with the P and Q, here we are going to obtain a bigger power, and we don't have control of that.
This energy estimate is something that all weak solutions satisfy, or that there is a weak solution that satisfies this. What's the statement?
For the theorem,
Because in the uniqueness you can fusion it.
yes.
So that means that all weak solutions satisfy this.
Well, the weak solution. Oh, okay, yeah. Well, I'm not sure if I understand because it's unique. So Leray solutions are weak solutions that satisfy this inequality. No?
Okay, so that's in the definition of weak solutions.
For Leray, I think so. No? So Leray how weak solutions are weak solutions that satisfy the energy inequality.
This is what's
And this is uniqueness.
the uniqueness
in that
of these Leray solutions.
Yeah.
There is always. I'm sorry, but I thought that the theorem of Leray just said that any L2 solution satisfies this inequality.
No, I think it's the other thing, but
It says so the statement should be read that there is one solution that weak solution that moreover satisfies this inequality.
I think so. I think that's the statement that. Yeah, because there are other. That's what I think. That there are other weak solutions for which non-uniqueness is known in 3D.
Or even start with the consideration solution that don't satisfy the inequality. Let's forget about me.
Yeah. Okay. But so what else? Okay, so now just go over the.
But for example,
Yes.
uniqueness is not known. There is
It's almost a play problem.
well, it's as much as we can get with no solution.
Yeah. And yeah, it's open, so I cannot say much more than this. That if you try to do this, which is not like a straightforward way of trying uniqueness in 3D, I checked the exponent here is theta 1,4, so this doesn't close. So I don't think I have too much time, so I'm not sure. I'll make a paper. But yes, the thing is that I'm not sure exactly. I haven't read the paper, so but
this is a paper from like 2 months ago.
Yeah.
People are
and this one it proves non-uniqueness, no, for a modified version of Navier-Stokes. Okay, I think in fact I will just stop here. My intention was to prove, but I think I will leave it, and probably next day I will start from the best of the spaces part. But basically because the proof of this, which I will decide if I comment at some point or not, follow the same steps that we've done twice, like find a fixed point argument, use the convergence and all that. The main difference with what we have done today is that in the construction of the fixed point argument at the beginning, you don't put the Laplacian as a perturbation, but you use fully the Laplacian. So when you have the equation and with some modifications, you solve the heat equation and you construct the fixed point on that with that function. Since I will do those things in more generality for critical spaces, I don't think it's worth to repeat it. And the part that it's slightly harder actually is to prove that the energy, this part of the energy inequality, that the solution that you construct satisfies. But yeah, I will just stop here.